All right, we've already talked about mechanical waves where you have to have a medium for the wave to travel through. So we need to talk about some other kind of waves, like a very important one you're going to run into in AP2 a lot is this the electromagnetic waves, how to make them and how they differ from each other and how are they the same thing. So here we go, electromagnetic radiation. Well, one thing, you don't need a medium for this. Okay, so electromagnetic, they're transverse waves, so they do not need a medium. They can travel through empty space. So a medium actually slows these down. For a mechanical wave, the medium, the more dense the medium, usually the faster the wave travels. It's kind of the opposite of electromagnetic because they don't need a medium. So a medium slows them down. So that's how your glasses work. Because when the wave slows down and it comes in at an angle, it actually bends or refracts, and it can in a position with where how the image is coming into your eyeball to help you see better if your eyeballs aren't perfect. Okay, so they are transverse waves. So they have a crest, they have a trough, and let's talk about how do we make this transverse wave. Well, you make them by basically vibrating a charged particle. In this case, they've taken a charged particle and gone sideways. They vibrate it this way, so the electric field goes this way, then they vibrate it the other way, the field goes the other way. So they vibrate it back and forth, back and forth, back and forth. And actually, if this is an electron moving, it'd be just the opposite because the electron is not a positive charge. But the point is, whenever you alternate or have a moving electric charge, it also makes a magnetic field. You're going to learn that in your AP2. But this magnetic field is perpendicular to the electric field. Okay, so let's take a look at how that happens. How do you make electromagnetic wave? Okay, so it's really a vibration in electrical and magnetic fields. Not vibrating particles, you're vibrating fields. Even as the light passes through your glasses or the window, you're basically vibrating charges as it comes through is what you're doing. It slows it down a little bit. Um, Okay, so let's talk about how in the world do you make these kind of things. So there it is. So you have basically a charged particle moving back and forth, back and forth, back and forth, and it varies the electric field. Let's look at a better example of how this works. Let's go to make a radio station here. Okay, so when the electric field changes, so does the magnetic field. That's how you get your electromagnetic wave. So you have an electric field in one direction, your magnetic field in this case in red in the perpendicular to that. Here's how you make one. We're going to go to KFET here out of University of Colorado. All right, coming up, coming up, coming up. And we actually had the simulation up already. Let me see if I can just pop up that simulation already. Oops. Oh, let me try that again. So here we are at KFET in lovely Boulder, Colorado. We're going to listen to a station 98.7. So for this radio station to make a radio wave of 98.7 megahertz, they basically take these charged particles, electrons, and they vibrate them. They vibrate them back and forth, back and forth, back and forth, back and forth. I'm going to get rid of the electric field. It probably looks a little confusing right now. Okay, so what happens is with a stationary charge, there's no varying electric field. There's an electric field around this thing, but it doesn't vary. But when you shake it, it does make a field. Not only a field, okay, I will just leave that on there. So what happens is I'm vibrating the electric field up and down, up and down, up and down, up and down. And by vibrating that field, you have a magnetic field that's perpendicular to that. But look what happens to that you're at your house over here on the mountains up there. Well, nothing now. So as long as they're broadcast, as long as they're shaking these electrons, and if they shake them at 98.7 million times per second, it sounds tough to do. It's actually electrically quite easy to do, to shake this back and forth at 98.7 million times per second. What that does is that wave radiates out through space in all dimensions there. That causes charged particles in the conductor to vibrate. Even your body. Somebody standing here or anywhere is going to have electrons vibrate just like that. And you could use your body as an antenna and tune in to 98.7. And if you had something electrical to convert that radio wave into mechanical wave, but you have to convert it from one kind of wave to the other, you can make sound. Okay? But that's how you make radio waves. That's how you make all electromagnetic radiation. This is the low energy stuff. To make the higher energy stuff, you got to shake it faster than what I can shake and what this radio station can shake that. But that's how you make electromagnetic radiation. You change the motion of these charges going back and forth. Well, thanks, Austin, for popping up right in the middle of our show. We appreciate it. Well, let's get back to the PowerPoint here and get away from Austin's text there, or message. So they all travel the same speed, 300,000 kilometers per second, which is 300 million meters per second. So that's 3 times 10 to the 8th. In a vacuum, even in air, it's still to 3 sig figs. It rounds off to 300,000 kilometers per second, or 300 million, or 3 times 10 to the 8th. Good number to memorize the speed of light because you use it so often. Okay. So they all travel at this speed, and because of that, in 1 second they go around the world 8 times in a second. So there you go. A little bit of fabulous knowledge. It takes 8 minutes to get clear from the sun, because the sun's very far, far away, but all electromagnetic radiation travels the same speed because they're all the same. They're all made by a vibrating charge. Okay, they're all made the same exact way. Alrighty, let's keep on rolling. So waves are particles. What are you going to learn when you hit your AP2? When you hit the modern physics, they can act as both. However, the low energy, the radio waves that on the lower frequency, they tend to act more like waves all the time. You get to the higher energy, the gamma stuff, it tends to act a little more like particles. But they all have wave characteristics. So we can call them a wave, but you'll learn in the AP2 how they can also be particles in the modern stuff. Okay? So it turns out being transverse, you can actually have a filter on that, and you could kind of filter out some, if they're a polarized light coming in like this through the filter, learn about how polarization works, how it can dim the light if it's oriented in a certain direction. That's how it shows, one way that shows it's a wave. But there's a photoelectric effect where a wave can come in and knock a particle loose, so it acts like a particle coming in. You can learn more about that in your AP2. We're not going to go into it here. So here's the story. You have your radio waves clear up to your gamma. This is the easier stuff to make because you don't have to vibrate it quite as quickly. This is the lower frequency. Remember, they have the same speed. Gamma travels the same speed as radio because it's the same kind of wave. The difference is the frequency and wavelength. Just like your bass, if you're bassing out in your car or whatever at home, the bass is longer wavelengths. They don't travel slower than the treble stuff, the higher stuff. It's all the same speed. But they have a longer wavelength but a lower frequency. So a long wavelength but small frequency. These have a high frequency but short wavelength because the wavelength and the frequency are inverse of each other. They all travel the same speed. Same story with this stuff. You have radio on the long end, gamma on the short end, and all this stuff in between. Okay, let's talk a little more in particulars about some of these. There's your radio waves, there's your microwaves, they're infrared, visible as you get shaking it faster yet is your ultraviolet, but here you're finally shaking fast enough it's getting a little dangerous. That's why they're slathering up some sun stuff on there. Visible light, not going to hurt you. Ultraviolet finally can be ionizing energy, and it can be dangerous to your body as well as the X-rays and the gamma radiation. But down here, not so much. That doesn't mean you can't make a laser light and burn holes through things. You can. You can burn holes with infrared lasers if it's a high enough concentration. But in normal concentrations, this stuff is not harmful, especially 1 photon is not harmful at all. 1 photon of this actually can be harmful. You'll get hit by more than that, but 1 can be because we just started getting high enough energy where it can be a little dangerous. Alrighty, and there's the gamma at the end there. Alrighty, so what the difference is, these are the size of buildings, these radio wavelengths, into their human size for your FM. Honeybees are in the microwave length, like the police radar and smaller, and even your phones work in the microwave region. Infrared is temperature, things are getting hotter. You can't see any light given off, but you might be able to feel that heat energy from something. Visible light, you get on the red end, it's very close to the infrared. Infra means below, so below the red. So red, we have detectors that we can measure a very narrow band of electromagnetic radiation with our bodies. And that very narrow section is a visible light on the red, clear up to the blue, the purple. Then above violet, or ultraviolet, finally getting energy, high enough energy that it can be a little dangerous. So also you can learn about in your optics, the reason we can see all of this really well is because the wavelength of light is smaller than that. These things are smaller than the wavelength of light. You can't use a light to see these things. You have to use different technologies with smaller wavelengths to try to see some of those things, or at least try to image those things. You get more of that in your AP2. All right, keep on rolling here. Oops, there's a whole spectrum I just zoomed right on past. So that's what we just talked about, size of soccer fields to baseballs to this period and cells, and finally we're getting to visible light near the bacteria. Viruses too small for us to see, but with ultraviolet they're getting to be about the same size. Proteins, to see proteins we need really higher frequencies or shorter wavelengths to really try to image those things, and we don't really image this very well because it's just hard to do. Okay? So this is lower energy stuff because you don't have to shake as hard. This is high energy stuff. Just like on a slinky, if you're shaking that thing, it's easy to shake slow. That's low energy. But to get it fast, that's it takes a lot more energy to make the thing go fast. Same thing here. It's higher energy to make these things than it is on the other end. All right, let's keep on rolling here. All right, so radio's the longest. It's the easiest stuff to make. We use that for a lot of communications, even for your satellites or GPS. Sound is not radio waves. They're two different things, but it can pick up a radio wave and convert it into a mechanical wave. But it's a little complicated, the conversion. It's not just a direct thing. There's stories of people picking up radio stations with their teeth. It doesn't happen that way. We don't have anything in your teeth to change that from a radio of a radio frequency into a sound frequency. That just doesn't happen. MRI, okay, still using radio waves and microwaves. We're getting heat in our food with that because we're causing the molecules to vibrate back and forth. Radar, police radar, infrared, getting warmer. You can image things, the things that don't give visible light. You can change that into something that we can see, a spectrum, to see different higher frequencies versus lower frequencies of infrared. See how hot things are, called the thermogram. Visible lights, we know a lot about that. We see stuff, it's in between the infrared and the visible. So red is the longest, it's the lowest energy. Purple is the highest energy, going a little faster. We'll learn about how that stuff works in your AP2. Ultraviolet, a little more energy, getting a little more dangerous. Can kill bacteria and sterilize some things and cause some damage to your nose there. So it also helps you make vitamin D though, so it's not all bad. Now we're getting to higher energy X-rays. You'll learn about how to make X-rays in your AP2, and how the whole X-ray thing works and why they're wearing protection. How they can use X-rays to examine building materials to look for cracks. Gamma ray. You need nuclear reactions basically for the gamma stuff. It's such a high energy. You need a lot of energy per little particle thing happening, and you only get that with your nuclear experiments. Okay, so you can also use that to treat different kind of things as well. But that's all. These are all topics for your AP2. What you really have to know is the difference between the radio and the gamma. And also with gamma radiation, you can make the Incredible Hulk, of course. Okay, so nuclear stuff is how you make the gamma radiation. So here's your brief summary. They all travel the same speed because they are all the same thing. Just like your bass, your low notes travel the same speed as the high notes, and with mechanical waves, because those are all sound vibrating the same air, as long as you're not changing the medium, this is how fast the light travels. It travels slower through water. It'll slow it down some, but through the air and through the space, the 3 sig figs, it's 3 times 10 to the 8th. And they all have different wavelengths. That means they have to have different frequencies because they all travel the same speed. So the higher the frequency, the shorter the wavelength. And the higher the energy, the higher the frequency. They are harder to make, and it can get a little more dangerous. That's in a nutshell what you have to know about your electromagnetic stuff for your AP2. There you are. I'll let you read on your own.